today we're happy to have Roman. He will tell us about Morse theory of loop spaces.
Yeah, thank you. So first of all, thank you for the opportunity to about this story. It's all based on the joint work with Honda, Yin Tian, and Tianyu Yuan. So let me start with the definition due to Morton and Samuelson. So to the surface, we can associate the so-called braid skein algebra, the skein of sigma. And we're thinking here about a punctured orientable Riemann surface. So this is a model over the round polynomial in two variables generated by isotopy classes of A braids, subject to the following relations. So first, we have a HOMFLYPT skein relation, which looks like this locally. And second, there is this punctured point skein relation. So we really think of these braids as k+1 braids, where there is one constant string going through this puncture. So if you sort of want to go around this puncture, you have to pay with c squared for this. So I'll explain in a moment the sort of reason for this second relation. But these braid skein algebra, they defined in order to study the more kind of standard skein algebra, which is just generated by links which are closed. And this is sort of more open story, and there is a natural way of mapping this thing into the skein algebra by closing the braids. And for just the standard skein algebra, they earlier showed that it's for the torus, it computes the so-called elliptic hole algebra. The product is given just by composing braids. So maybe pictorially, these generators looks like this. So this is our torus. Maybe you have k points here. So each generator Ti is just the standard generator in the braid group. Just nothing happens at these k points, and at point I and I+1, they're being swapped. And x1 and y1 are just the generators of the pi1 passing through the first of these points. Okay, so that's x1, this is y1, and then there is a bunch of points here and here. So they compute this whole thing, and this presentation actually gives us, so this whole thing is GLK double affine Hecke algebra. One can see from this presentation and equating it with any other maybe more famous presentations. So let me just say quickly what's happening here. So these are standard braid relations for the braid group generators. Here is how they act on x1 and y1, so how you can commute x1 and y1 with these TIs. This is the sort of standard Hecke relation, which tells us how to compute the square of TI in terms of lower terms. And well, this is additional relation for commuting x1 and y1. Okay, so now so why maybe one can care about this. So some interesting appearances of DAPA and why one may care about these braid skein algebras for other surfaces. So first, famously, it showed up in Veridnik's proof of McDonald's constant term conjecture. Second, it is known that it computes equivariant case theory of the Steinberg variety affine type. This is a result of Bergnola and Basserot, which generalizes more classical result of Kashdan and Lustig in just the standard case where fine Hecke algebra computes the corresponding K-theory. Then it's also known that it's related to Algebra Moser systems, which describe quantum many-body problems in one dimensions. And finally, it also admits description as a description as orbifold Hecke algebra of the symmetric cave product of a torus. This is due to Ettingolf. Maybe going back to 2004, but this particular statement appeared later, but ideas are laid out there. Okay, so the question we're sort of trying to answer is how to recover these braid skein algebras via Floer or symplectic geometry. So sort of a categorification type question, and well, earlier people answered similar questions for invariants shown up from quantum topology. So instances are symplectic Lagrangian homology, due to Seidel and Smith, and Anlesco from 2006, and later Abzeg and Smith showed that indeed over characteristic 0, this construction recovers on homology, and they did it only as a graded model, and then the later work of Chen shows that as a bi-graded model, you can recover via this construction the symplectic homology. Second, more recently, there has been introduced an approach to annular homology due to Acid and Krutowski and Sikora in works of Mack and Smith. And Morris and Hendricks. And Robin. And well, in some sense, they are studying Floer theory of the corresponding Hilbert scheme, and at least our approach has to do with symmetric product of the cotangent bundle, and morally these two stories should be related. Okay, so
Can you
yeah.
say for symplectic homology that will correspond to sigma b?
Yeah, I mean, right. So you just take any link and say S3, and by looking at the Hilbert scheme of C2, but you throw away some divisor, and to a link, if you have some braid presentation, you can associate two Lagrangians in the Hilbert scheme. So these invariants are just Lagrangian Floer homology for a certain construction in this Hilbert scheme. But yeah, I mean, like, it's described in more details in these works. I mean, yeah, there is also a work of Yuan, which sort of hints that whatever I'm going to tell you about may recover symplectic homology if you look at this at a particular perspective on it. Okay, so yeah, I don't want to erase that board yet. In 2022, on the and Yuan showed that for sigma with genus at least one orientable, the infinity higher dimensional Heegaard Floer homology actually recovers these braid skein algebra. So I'll tell you later what this higher dimensional Heegaard Floer homology is, but the result says that if you take sort of K tuple of cotangent fibers in sigma and compute some infinity algebra, this was isomorphic to the braid skein algebra K sigma with the specialization H bar equals S minus S inverse. So we need to change these variables, and the result only works over actually power series in H bar. So here Q is just an element in the configuration space, which is just a complement to the diagonal in the cave product of sigma with itself. And so sort of remark here for this result is important that sigma is a K pi. So yeah,
Can you explain the object on the left a little more? You said this is chains on the base of space.
We'll get it, but I'm saying that there is some kind of, yeah, so how you should think about it is morally. That this thing is a like cotangent fiber in the cave symmetric product of sigma. Although, well, for sorry, yeah, cotangent bundle of the symmetric product. So this is an orbifold, and we're just computing Lagrangian Floer homology of this fiber with itself. But I'll explain a little bit later how you can set up.
Oh,
this, sorry.
This is some kind of wrapped Floer group. It's like
Yeah, this is like Lagrangian Floer homology, but yeah, I'll explain how this variable shows up because it's.
I just didn't understand the notation.
I'll explain a little bit later.
And the homology of both sides, and compute the singular homology of the loop space on symmetric product. Is that right?
Unfortunately, no.
Okay.
Yeah, so maybe from like these Etingolf's perspective. So this Dacha is a deformation of the group algebra of like of the pi1 of the symmetric problem. So it's a certain deformation because you have this variable h bar, which is kind of formal, and okay, there are two variables there. So these are formal variables that you kind of initially don't see just from the topology. So you add certain deformation by looking like, but like deforming your initial, yeah. So maybe the most important thing is this quadratic relation. If you put s minus s inverse to 0, it just says t1 squared is equal to 1. And this is what you have there because it's kind of corresponds to going around the diagonal in the symmetric product. So in the orbifold sense, because it's like Zemo 2 point, square should be equal to 1. But you kind of deformed in this formal way, and representation theorists tell us that this is quite interesting algebra that you obtain. So this thing will be like a deformation of the homology of the loop space of symmetric product. Okay. Yeah. So right. So maybe again going a little bit ahead. It's important that it's a k pi 1 because we sort of understand everything about say Hamiltonian chords in the cotangent bundle of the k pi 1. They just correspond to generators in the pi 1. There will be no really A infinity algebra structure here. They just, like for this theorem, just need to compute the product, and this is nice. Okay, so the theorem that we prove now that the this invariant that I'll explain in a second for the sphere is quasi-equivalent to the DGA HA, which is, yeah, and then here I'm sort of specializing to the C being equal to 1. So it's generated by variables T1, etc., Tk minus 1 and x1 subject to the following relations. So here now Ti's, they're all in degree 0, and x1 is in degree -1. And well, you sort of may think of this new generator as corresponding to going around the equator once, which corresponds to a non-trivial generator in a sort of Morse-theoretic approach to computing homology of the base loop space of S2. And again, sort of in k equals 1 case, this would just recover, putting h bar to be equal to 0. This just recovers homology of the base loop space of S2. Okay, so yeah, so kind of these are sort of slightly trickier relations than the other ones. So this is like the quadratic relation that was here before, just rewritten after this change of variables. And you have braid relations from before, and well, claim this is all you need. In particular, H0 of HK is just isomorphic to the braid skein algebra of S2, where you specify h bar to be equal to S minus S inverse and C is equal to 1. So this invariant that we obtain this way here kind of sees more and then what the skein theorists tell us, and it would be interesting to see an interpretation of this derived invariant from quantum topology perspective. Okay, so let me now try to answer those questions about what these higher dimensional Heegaard Floer homology are. But maybe are there any questions at this point?
In this case, is the homology supported in degree 0?
Yeah. In the k-pi1 case, there are no interesting Hamiltonian chords or generators in the homology of the base loop space. They all sit in degree 0 and correspond to generators in pi1. Whereas, at least in the case of S2, we have like going around the equator however many times you want, giving you generators in each degree. All right, so the idea here is that you can define a certain, you can use cylindrical interpretation going back to ideas of Robert Lipshitz to interpret the Lagrangian Floer theory of the symmetric product. So to do that, first I'll do it for just the cotangent bundle and the cotangent fiber there. So let me denote this way is disjoint union of cotangent fibers. So I goes from 1 to k, and Q here is an element in the configuration space of M. And I'm assuming that M is orientable manifold, not necessarily of dimension 2. Then CW0 E star M would be just k tuples of Hamiltonian chords starting and ending at this kind of k tuple of fiber, but we allow them to make some permutation along the way. So formally can be written as a direct sum over elements in the symmetric group of the following tensor products. So just standard generators in the Rhodes-Fokker category. So kind of pictorially, you may have, say, these two fibers, and your Hamiltonian chords may either like start and end on them, or they may kind of go here and here. It's very schematic picture. So this will give us this pair corresponds to sigma equals identity, and this pair corresponds to sigma being equal to the transposition. Okay. Now, to count the infinity operations, we first introduce our moduli spaces of domains, which is sort of all Hurwitz type moduli spaces. Because they're basically spaces of certain k-fold simply branched covers. So first, let me denote by RDB moduli of d+1 punctured disks with B markers. So these markers are interior ones. So these are these B markers. And we have, say, these punctures on the boundary. So here D equals 3, B equals 3. And then this is sort of the standard kind of moduli spaces showing up in the Fokker category. But then we are interested in k-fold covers over such disks. So this sort of whole picture belongs to the moduli space RD KI moduli of k-fold simply branched f b equals k minus I points with I of f being equal to this fixed number chi. So this is just Riemann-Hurwitz formula here. So we will consider this moduli space of such k-fold covers, and we'll look at like curves from an element here to our cotangent bundles, and at each like pre-image of this point there are k punctures, and then we have k limiting conditions to the corresponding k Hamiltonian chords. Yeah.
So for each sigma, you're considering it different, right? Right.
Yes, I mean, I'm just picking the sort of standard quadratic Hamiltonian on the cotangent bundle. So here H is maybe like 1/2 b squared. Okay, and yeah, maybe maybe for some technical issues you would want to perturb it a little bit, and for each qi to have its own slightly perturbed Hamiltonian. But yeah, let's ignore these details.
But once I fix sigma, it's fixed. Like
Yeah, once you fix M and its cotangent bundle, it's all fixed. Okay. And any other questions here? Okay, so then the moduli spaces that we count are as follows. So if you have y1, y not corresponding a tuples of course, we associate with it the moduli space M K chi 1D to y1. Is here being the the space of U equal by B from F dot to D dot times T star M, such that, well, a bunch of relations, but first this pi belongs to our moduli space. Second, B of perturbed d bar j equals 0, and finally at pi inverse of puncture, so the ith puncture convergence to the chord yi. And perturbed means actually there is some Floer data over peaks over these moduli spaces, and we count solutions to these perturbed solutions, to these perturbed equations. So that's sort of how you obtain the infinity operation. So the formula would be, if you pick these d chords, is the sum, or why not, and pi of time counts of elements in these moduli spaces divided by a minus chi factorial, then multiplied by the power, the h bar to the power kappa minus chi times y naught. And these are all sign counts. So I think, yeah, I forgot to write something here. So the model, the whole model that we are interested in is the sort of formal completion of this model with respect to, let me write Q for now. This is a formal completion with respect to this. No, sorry. Yeah. So an h bar here is a variable in degree 2 minus n. So when n is equal to 2, you just get power series in h bar. If n is greater than 2, you get sort of rightly graded power series in h bar. And the reason for this is sort of the dimension of this moduli space is counted. Well, first you have the usual contribution. And then you subtract n minus 2 times k minus chi. So when n is equal to 2, this actually doesn't contribute. And that means you may count curves of arbitrary high genus. In case n is greater than 2, you actually can control like how big of a genus you need to account for given chords. Okay. Any questions here? Okay. So now the question is how to compute this thing. And for this, we introduce this kind of Morse-theoretic model, at least for the cotangent bundles. We don't claim that we know how to compute it for any Liouville domain, but this can be defined for any Liouville domain. Okay, now let me briefly tell you how one can do Morse theory on in path spaces. So these ideas were introduced in works of Abundando and Meyer and Abundando and Schwartz, and we kind of use their approach to obtain those kind of computations. So first, you fix the smooth Lagrangian, which is quadratic fiberglass, quadratic and convex. So here we're assuming some, so this M is now Riemannian. We picked some symmetric, and yeah, so quadratic along the fiber just means that, well, you may have some terms like norm of v squared, norm of v, but not norm of v cubed. So, so an example here is just the standard 1/2 of the norm squared, and these in a second will give you geodesic paths or loops. So on omega 1 m q prime, which is the Sobolev path space, this is W12 paths connecting U to Q prime. We have the action functional AL of gamma being equal to the integral from 0 to 1 of L T gamma dot T dt. So yeah, this is just a function from this space, real numbers, and the critical points of this functional are the solutions for the Euler Lagrange equation. So for this particular L, you recover geodesics for this Riemannian metric. Now, the problem is that you actually cannot do Morse theory so easily for this function on this Hilbert manifold, for instance, because this function is not even C2, depending on, well, at least not for any choice of L in this set of quadratic, fiberwise quadratic and convex Lagrangians. But Abundando and Schwartz tell us that you can sort of always pick a nice vector field to run Morse theory. So there exists pseudo gradient vector field X on this path space for one Morse theory of A. So what it means is that first critical points of this vector field coincide with critical points of this functional. Second, unstable and stable manifolds, they intersect transversely. And most importantly, the computification is obtained by the moduli spaces of piecewise pseudogradient trajectory, which requires this so-called Pelez-Mail condition. And additionally, have the following lemma that it will be important. So for any critical point gamma, we have that unstable manifold of gamma with respect to such x actually sits inside of smooth paths connecting Q to Q prime. So this is sort of elliptic regularity for the Morse theory statement. Okay. So now we want to mimic this story that we see on the Floer side. So most importantly, we'd like to understand how Morse theory can see those branch points. That's kind of the main problem. But yeah, these points.
So can I ask a question about the branching point? So you said the moduli space only has simple branching points.
Yes.
You have to compactify.
Yes.
Okay. So you will tell us how that looks in the path space.
Yes. Okay. Thank you. Yeah. Okay. Yeah. You maybe what should I say? If you want to add like more interesting branch points, you actually need to add some additional variables, because kind of if you have a trickier branch points, that means it would contribute kind of the index formula differently, and in general would cut out more dimensions. We don't do that, but in theory, one can do that. Okay, so so now, as like in this picture, on the zero section, we just consider spaces of paths from these k points to back to the same k points, but maybe with a permutation along the way. So fix these k couples and omega m2 paths from one tuple to another is just disjoint union of similar m2 path spaces in the cave product from Q to sigma of Q prime. So again, in the A=2 example, say you have these points around, so you may have these kind of path, connected component, and maybe this one. So the blue tuple of paths sits in a separate connected component from the white one. Okay, so if you do Morse theory of this thing, so far you don't get anything new. And coming back from Augustine's question, you will just get homology of these loop spaces and maybe like tensored with the group algebra of symmetric problems. So like many copies of it. Now, I would like to introduce those whatever branch points on the Morse side. And the idea is to use some analog of Chas-Sullivan string bracket, but in this kind of phased loop case situation. So first, let's observe that for a fixed pair of distinct elements and among like 1 through k, we have the following submanifold inside I times omega into u prime, which consists of, so this is just 0, 1, which consists of pairs theta and tuple of paths gamma, such that gamma I of theta is equal to gamma j of theta, and sort of in the orbifold kind of language, you can say that this gamma of theta belongs to the fixed point set of the action of the transposition ij on the case product of them. So this is a Cm-1 submanifold, and this is sort of the reason why I started writing omega m2 and requiring more regularity on this. And the reason for that is that you kind of need to take derivatives along this theta because you a priori don't know at what moment you intersect. So pictorially, this looks like this. So you have gamma I, gamma j, they intersect at this moment, gamma I, gamma j, and well, any other path may do whatever it likes, so it doesn't have to intersect. Now the idea is that when they intersected these two paths, you can kind of replace these two paths with another one where gamma I first travels until the intersection point and then jumps to gamma j and goes here, and similar thing happens to gamma j. So that's exactly what happens in the string bracket operation of Chas and Sullivan. So formally, we have these switching maps J from delta ij to itself, which sends theta gamma to theta gamma restricted to 0 from theta, and then concatenated with ij acted on gamma restricted to theta to 1. Now this basically formal way of writing what I just showed here in this. So ij does not affect any other path besides gamma I and gamma j. Okay, and now the moments along the trajectory where you sort of hit this diagonal and then further application of this switching map are our analog for the branch points. So theorem here that we prove that there is an A infinity algebra structure on Cm minus R. This moment on M prime, which is again the kind of a deformation with respect to this formal variable. And variable is again equation 2 minus n. And this is just the model generated by tuples of geodesics or tuples of critical point given by counting Morse, so-called Morse lines in trees with switches. So I'll just draw a picture here. You may have some kind of trajectory like this, and these places are where you intersect with this diagonal, and sort of for each path gamma j along this trajectory, the main condition is that switch and map applied to, say, corresponding permutation ISJ with theta gamma j H LG, where let's say this is a map from 0 L1 to our space of paths. So the condition is that the switch map for the J thing should land at the start of the next trajectory. So kind of when you hit the diagonal here, you apply this switch map and you keep on going. And the Morse flow trees, they look like this. So you may have a bunch of initial tuples of geodesics, then you kind of flow. Again, whenever you hit something like this, you apply the switching map. Whenever you hit a vertex, you concatenate. Okay. Any questions here?
I don't really, what's the geometric nature for the switching map?
Yeah, so maybe I should just draw it here. So gamma j gets replaced with something like this, and gamma I gets replaced with something like this. So you kind of just jump from gamma I here onto gamma j at the moment where they intersected. So that is this theta that we keep tracking. And you go and you keep on going on gamma j. Sounds good. That's sort of, yeah, so that goes kind of to the old idea of Foucault a bit. If you sort of have some disk like this, you can either travel this way and this way, or you can travel this way and this way. There is sort of, this is the boundary of your disk with the node. There is ambiguity of sort of evaluation map along the boundary. So here on one side, you have this kind of way of traveling and saying that this was the path gamma I and this was the path gamma j. And here you're like, okay, that maybe I wanted to travel here after this junction.
I guess I wanted that. You knew the branch point was there?
Yeah, because it's a map only from this diagonal to itself. So it's not the map from any multipath, but only from those where you kind of said that they intersect. And that's sort of yeah, so maybe I should say the dimension count of these Morse full trees. Again, some standard term, which maybe I won't try it, but minus n minus 2, and let's say there were like L of these moments. So minus n minus 2 times L. So each time you intersect this diagonal, that's co-dimension n minus 2 condition. So if n is bigger than 2, then if you fixed your geodesics, then you know that you will not switch more than fixed amount of time just by index considerations, which is not true for n equals 2 again. So that's why we need power series. Okay. So yeah, let me maybe state the comparison theorem for the cotangent bundle and say briefly how we do computations with this Morse model. So theorem reason there is a quadrant equivalence at from the Floer side to this Morse model. And this is given by counting things like this. So F1 counts maps which are covers of half of the disk with the boundary condition. So this particular preimage of this particular boundary is sent to M, and the whole thing is sent to T star M. And here you evaluate at this boundary, so you land on M, and then you get this like half of Morse full line with switching. So you start here and you keep on going. And similarly, higher infinity maps count something like k-fold covers over some caps, and then trees trees at the bottom. And the main, the main crux of the argument is showing that you can trade these range points for switching points and vice versa. And that goes to that picture, but maybe I will talk about computation. We get back to this.
Since I don't like the abandon of shorts.
Right. So if you put k equals 1, that's actually Bose-Eid's map, but it doesn't matter because Abodando and Schwarz first kind of show that this is an isomorphism, and this is an isomorphism as well because it's kind of the inverse one, right? So, and yeah, this result is also important for showing that this thing is an isomorphism because this map is kind of, if you put h bar equals 0, you just count things without any switchings, and you know that best thing is an isomorphism by results of Bose-Eid and Abodando and Schwarz. And we use that to say that the deformation is when you have a functor and it's a deformation of some isomorphism, it kind of just some homological algebra has to be an isomorphism.
But that's a much simpler setting than the way you're.
Yeah, this is like more stuff going on here, and most importantly because you have like higher genus curves to count. If you don't have any switching points, kind of k-fold cover is just 3 copies of half a disk. And no switching points just means standard Morse theory. Okay, yeah, thank you. All right, so let me maybe just illustrate how you can get some of these relations for the sphere. Okay, so for instance, let's show that dx1 is equal indeed to something like this. So look at your sphere, and there is this, maybe I'll decouple end and start points as before. So x1 looks like this. So this is an equator going from this point to this point. These points are really close. Now the unstable manifold of this thing just consists of kind of some movie sweeping out left hemisphere and another movie sweeping out the right hemisphere. So if you look at the trajectory in the left hemisphere, well, it never intersects these strands. So there is no like switching moment to occur. But when you go to this side, at some point, you get to something like this. And as a braid, this looks like sort of the standard, not the standard, but the braid going around all these strands. And then there is a sort of, because we are in this low energy regime, then when you do the whole resolution and there'll be a lot of like switching moments, you can show that it resolves to something equivalent to this braid in a just braid skein algebra of the disk, because everything is sort of local. And this is just the braid presentation for this thing. And therefore, like looking at the homology, we get this additional relation that we need in like zeroth homology of the braid skein algebra of the sphere. The hard part, okay, maybe I'll say briefly. So the hard part is showing that you don't have any higher infinity operations, and for just standard metric on this two, we don't know how to do it, but we use Finsler metrics from cutoff examples to run some sort of action argument. Okay, maybe I'll stop here.
You mentioned that Yuan has some work that suggests how this might be related to symplectic homology.
Yeah, I mean, he has computations of this higher dimensional Heegaard Floer homology or invariant like this for like the Weinstein domains that you get by looking at this A singularity. And by sort of looking at the same Lagrangians, you get some invariant, and he has some computations for some links which are equal to Havana homology. But yeah, that work doesn't prove the isomorphism.
Yeah, there are no more questions. Let's think about. Okay.